What if complex numbers weren't the end of 2D algebra? What if there were infinitely many types of 2D number systems, each with its own unique rotation, geometry, and algebra? In this video, we'll take you on a journey from the familiar complex numbers to an original 2D system I call the Mokabic numbers, which rotate by 60 degrees. And then we'll step into the generalized 2D number system that allows for any degree of rotation. Let's dive in. Quadranian numbers, the foundation of 2D number systems. Let's start from what we already know, complex numbers, and I personally call them quadranian numbers. A quadranian or complex number is written as z equals a plus b times I, where a and b are real numbers, and I is the imaginary unit defined by I squared equals -1. This might look simple, but it has deep meaning. Geometrically, complex numbers live on a 2D plane, known as the complex plane. The real part A is plotted on the x-axis, the imaginary part B is plotted on the y-axis. So the complex number z equals a plus b times I becomes a point at coordinates a, b. Now here's the powerful part. Multiplying a complex number by I rotates it 90 degrees counterclockwise on the complex plane. Let's see why. Take a simple complex number, z equals 1 plus 0 times I. Now multiply it by I, z prime equals z times I, which is 1 times I, giving us I, or 0 plus 1 times I. Originally, the number was on the real axis at 1, 0. After multiplying by I, it's on the imaginary axis at 0, 1. That's a perfect 90-degree rotation. Now keep multiplying by I and you get a full cycle. I to the power of 1 is I, which is a 90-degree rotation. I squared is -1, which is a 180-degree rotation. I cubed is -I, which is a 270-degree rotation. I to the power of 4 is 1, which brings us back to the start at 360 degrees. So complex numbers rotate by 90 degrees per multiplication with I. This cycle gives us 4 distinct units on the complex plane: 1, 0, 0, 1, -1, 0, 0, -1. These 4 points form a square lattice equally spaced 90 degrees apart. This makes the complex number system a 2D number system with a 90-degree rotation defined by r squared equals -1, where the unit r is I. But what if we wanted a 2D number system that rotated by something other than 90 degrees? Say 60 degrees? That's where Mokabic numbers come in. Mokabic numbers, a new 2D number system with 60-degree rotation. Now that we understand quadranian numbers as a system with 90-degree rotation, let's take a leap into something original. The Mokabic number system. This is a new kind of 2D number system defined by a different rotation. Instead of rotating by 90 degrees, Mokabic numbers rotate by 60 degrees. Let's define it. We introduce a new unit called the Mokabic unit t and define it by the rule t to the power of 3 equals -1. Just like how complex numbers use I squared equals -1, Mokabic numbers are built on this cube root identity. A Mokabic number is written as m equals a plus b times t, where a and b are real numbers, and t is the Mokabic unit. Powers of t and 60-degree rotation. To understand the Mokabic structure, let's compute powers of t using the fact that t cubed equals -1. T to the power of 1 equals t to the power of 2 equals t minus 1. T to the power of 3 equals -1. T to the power of 4 equals t times -1, which simplifies to -t. T to the power of 5 equals t squared times t, which is t minus 1 times t. Expanding, this gives t squared minus t, which simplifies further to -1 minus t. T to the power of 6 equals t cubed squared, which is -1 squared, giving +1. Thus, multiplying by t rotates the number by 60 degrees counterclockwise. The repeating cycle is t squared, -1, -t squared, and 1. So we have 6 distinct units, equally spaced by 60 degrees on the 2D plane. Geometric representation of Mokabic numbers. These 6 units form a hexagonal lattice. Their coordinates can be written as 1, 0, 0, 1, -1, 0, 0, -1, -1, 1, 1, -1. Now we derive an important property. T squared equals t minus 1. This equation tells us that t squared is positioned at an angle of 120 degrees. Using the formula for the phase angle, theta equals the inverse tangent of the square root of 3 times b divided by 2 times a minus b. For t squared, where a is -1 and b is 1, theta equals the inverse tangent of the square root of 3 times 1 divided by 2 times -1 minus 1. Simplifying, this becomes the inverse tangent of the square root of 3 divided by negative 3, which gives an angle of 120 degrees. Similarly, for t cubed, which equals negative 1, we substitute a equals negative 1 and b equals 0. Theta equals the inverse tangent of 0, which results in an angle of 180 degrees. So, multiplying by t rotates by 60 degrees counterclockwise. Conjugate in the Mokabic system. In complex numbers, conjugation represents a 90-degree reflection. In Mokabic numbers, conjugation follows a 60-degree reflection rule. Since multiplication by t represents a 60-degree rotation, the conjugate of m equals a plus b times t must reflect accordingly. From our calculations, the conjugate is given by m prime equals a plus b minus b times t. For example, if m equals t, which corresponds to the coordinates 0, 1, then m prime equals t squared, which is t minus 1, corresponding to negative 1, 1, 1. This confirms that the conjugate is found by a 60-degree reflection across the real axis. Modulus in the Mokabic system. In standard systems, the modulus, or absolute value, is computed as the product of a number and its conjugate. The squared modulus is given by the absolute value of m squared equals m times m prime. Using our conjugate formula, m prime equals a plus b minus b times t. Multiplying m by its conjugate, m times m prime equals a plus b times t, multiplied by a plus b minus b times t. Expanding the terms, a squared plus ab plus b squared. Thus, the modulus of a Mokabic number is given by the absolute value of m equals the square root of a squared plus ab plus b squared. This result differs from the Euclidean norm, but aligns with the hexagonal structure of Mokabic numbers. Now let's try to express the imaginary unit I in terms of the Mokabic unit t. Suppose I equals a plus b times t. We want to find real numbers a and b that satisfy this using the rule that I squared equals negative 1. Squaring both sides, I squared equals a plus b times t. All squared expanding, a squared plus 2ab times t plus b squared times t squared. Now substituting t squared equals t minus 1, I squared equals a squared plus 2ab times t plus b squared times t minus b squared. Grouping the terms, I squared equals a squared minus b squared plus the quantity 2ab plus b squared times t. Since we know that I squared equals negative 1, we match the real and Mokabic parts. From the real part, we get the equation a squared minus b squared equals negative 1. From the Mokabic part, we get the equation 2ab plus b squared equals 0. Now let's solve this system. From the second equation, 2ab plus b squared equals 0, factoring out b times the quantity 2a plus b equals 0. This gives two cases. Case 1, b equals 0, which leads to a squared equals negative 1, which is not possible for real a. Case 2, 2a plus b equals 0. Solving for a equals negative b divided by 2. Substituting into the first equation, the quantity negative b over 2 squared minus b squared equals negative 1. Expanding, b squared over 4 minus b squared equals negative 1. Multiplying everything by 4 to clear the fraction, b squared minus 4, b squared equals negative 4. Simplifying, negative 3b squared equals negative 4. Dividing by negative 3, b squared equals 4 over 3. Taking the square root, b equals plus or minus 2 over the square root of 3. Now solving for a equals negative b over 2, which gives a equals plus or minus 1 over the square root of 3. Thus, we find that I can be written in terms of t as I equals negative 1 over the square root of 3 plus 2 over the square root of 3 times t, or I equals 1 over the square root of 3 minus 2 over the square root of 3 times t. This means the imaginary unit I from the complex system can be written entirely in terms of the Mokabic unit t, using real coefficients. That's a powerful result. Euler's formula in the Mokabic system. In the complex system, Euler's formula states that e raised to the power of I times theta equals cosine theta plus I sine theta. For Mokabic numbers, where the analogous expression are raised to the power of times the takeus are raised to the power of the ta over 2, multiplied by the quantity cosine of the square root of 3 over 2 times the ta minus 1 over the square root of 3 times sine of the square root of 3 over 2 times the ta plus 2 over the square root of 3 times sine of the square root of 3 over 2 times the ta tim stay. This describes exponential growth with hexagonal rotation. It shows that complex numbers are embedded inside the Mokabic world. And this is just one example of how different two-dimensional systems can be built from a shared logic. Now that we've built two such systems, complex and Mokabic, Let's take the next step. Let's generalize all two-dimensional number systems. Now that we've seen two different two-dimensional number systems, complex numbers with a 90-degree rotation and Mokabic numbers with a 60-degree rotation, it's time to look at the big picture. Can we generalize all two-dimensional number systems? Yes, and here's how. Let's define a generalized two-dimensional system using a unit r, with the rule r raised to the power of n equals -1, where n is a positive integer greater than 1. Just like before, we define a number in this system as z equals a plus b times r, where a and b are real numbers. The lower dimensional coefficients, r is the unit that rotates by an angle of theta, which equals 360 degrees divided by 2n. For specific values of n equals 2 gives r squared equals -1, leading to complex numbers with a 90-degree rotation. N equals 3 gives r cubed equals -1. Leading to Mokabic numbers with a 60-degree rotation, n equals 4 gives r to the power of 4 equals -1, leading to a rotation by 45 degrees and so on. Each unit r generates 2n distinct units. R raised to the power of 0, r raised to the power of 1, r raised to the power of 2, continuing up to r raised to the power of 2n minus 1. Since r raised to the power of 2n equals r raised to the power of n squared equals -1 squared, which equals 1. This creates a cyclic pattern of 2n steps, forming a regular 2n-gon around the origin, a full rotational cycle on the two-dimensional plane. Each system corresponds to a unique 2D lattice where the powers of r plot out evenly spaced points on the unit circle, separated by theta equals 360 degrees, divided by 2n. For example, when n equals 2, we get a square lattice corresponding to complex numbers. When n equals 3, we get a hexagonal lattice corresponding to Mokabic numbers. When n equals 4, we get an octagonal lattice, and so on. Each of these lattices defines its own algebraic behavior. Starting from real numbers, we built complex numbers using the unit I defined by I squared equals -1. That gave us a full 2D system with a 90-degree rotation and 4 units on a square lattice. Then we explored the Mokabic number system, with t cubed equals -1, giving us 6 distinct units, spaced at 60 degrees, forming a hexagonal structure. We didn't stop there. We generalized this into an infinite family of 2D number systems, using the rule r raised to the power of n equals -1. Each value of n gave us a new type of 2D number system, with its own geometry, its own units, and its own algebra. But the real magic? We constructed all of these systems using lower dimensional numbers as coefficients. And here's the big idea. If we can build 2D systems using 1D numbers, then we can build 3D systems using 2D numbers and build 4D systems using 3D numbers, and so on. Each level of dimensionality is built recursively, layer by layer, using the previous dimension's numbers as coefficients. This isn't just a new number system, it's an entire hierarchy of number systems, each one with its own unique algebra, rotation, and geometry. We call this idea dimensional algebra. It's a framework that allows us to generate new dimensions, define new kinds of numbers, and visualize algebraic structures geometrically, all from the ground up. In the next video, I'll introduce dimensional algebra formally. We'll explore how to construct 3D and 4D number systems using this method, and how quaternions appear as a special case of our 3D construction when n equals 2. But more importantly, we'll see how our framework goes beyond quaternions, opening a path to higher dimensional algebras no one has mapped before. So if you thought quadranion and Mokabic numbers were cool, wait until you see what comes next.